Prepare for a cosmic ripple.
And make that triple.
To study the phenomena of solar granulation.
To solve familiar things with a math equation.
To explore the unknowns of the universe thereof.
To look at the stars in the sky above.
Mason.
Ethan.
Team CMELLY does the astro reading at the speed of light.
Let's now learn about the sky at night.
Larry, that's right.
So we decided to do our project on exoplanet observation by Team CMELLY. So here is our table of contents. We are starting off with what exoplanets are, some background information, and then we're going to move into a brief history of exoplanets, then talk about detection methods, talk about our target, and then more on our experiments and our observations and results, and then finally what we learned. So first, what are exoplanets? What do they tell us? Exoplanets are planets that orbit stars other than our sun. Some conditions for exoplanets are that their minimum mass or lower bound of mass must be at most 30 Jupiter masses. And also exoplanets must not be free-floating, which means that they must be gravitationally attached to a star. So what do we learn from exoplanets? Well, from exoplanets, we learn more about planetary systems. So usually we opt to study our solar system to study planet formation. However, the data about exoplanets tells us that our solar system is actually highly unique compared to all other planetary systems as we can live here. Also, the study of exoplanets works to help better define our place in the universe, and it also helps us confirm whether our knowledge about planetary formation and systems and general processes that we learned just from our solar system studies are valid. Further, in studying exoplanets, astronomers are also interested in finding extraterrestrial life. We study whether the planets are habitable, and we have what's called the Goldilocks zone, which refers to this habitable zone around stars where the temperature is just right for water to exist. And then here are all of the discovered habitable exoplanets in order of distance from the Earth. And this is just an artist's conception made in 2020. Now let's talk about a brief history of exoplanet discovery in astronomy. Here's a very brief timeline. In January 1992, astronomers Alexander Wolszczan and Dale Frail found the first two exoplanets on the pulsar star PSR B1 257 plus 12. This system is about 2,300 light years, or around 700 parsecs away from the Earth. And basically, this as a pulsar, there was supposed to be regular radio wave pulses, but they were observed to be a little off every once in a while. A little more studies showed that these disturbances actually also occurred regularly, and they ultimately found that there were two planets and their gravitational pull affected the pulses with the regular period. Then, in 1999, the first transiting exoplanet, HD 209458b, was discovered on the star HD 209458. This was the first use of the transit method for exoplanet discovery, and the system is 159 light years away. In 2011, Qatar-2b, our target for this project, was discovered. And today, our group tries to find an exoplanet with the TMO telescope. More generally, the astronomy field is moving towards an interest in characterizing the discovered exoplanets and assessing their habitability. Here is the number of detections of exoplanets over the years from NASA's exoplanet archives depicted in a graph. As of January 2021, we've already discovered 4,341 exoplanets, so quite a lot. And here is also a nice picture from 2019 of all of the exoplanets mapped in the night sky. It's color-coded by discovery method with the legend in the top left and right corners. And this is also from NASA data, and it's also an artist's conception.
So next, I'm going to talk about some detection methods of detecting exoplanets. And we're going to talk a bit more about our method of choice. So there are multiple methods. The first one I have here is radial velocity. And in this case, we measure the Doppler shift of our host star. So we have our host star, and then there might be maybe a red shift or a blue shift of the star spectrum. And in that case, we would be able to tell that there's an exoplanet there. And then for another method, there's also gravitational microlensing. One of the big downsides to it is that it's pretty uncommon, but it's very, very useful if it comes into effect, because when there is a lens star, which lenses the star behind it, which has an exoplanet, then there would be a massive dip in the brightness of the star. There's also pulsar timing, in which case there is a change in the pulse of the radiation of the pulsar, which was kind of explained earlier. And then, so for our experiment, we used transit photometry, which basically you take images of a star and then you measure the dip in brightness of that star, which is due to the exoplanet moving in front of it. So next up, we're going to talk about our target, mainly how we chose it, and also our procedure. So our target that we chose was Qatar-2b, which is roughly 600 light years away. And so the magnitude of Qatar-2, which is the star, is 13.30. And then the dip in magnitude is supposed to be 0.0374, which is roughly 4% dip. The distance from the star for Qatar-2b is 0.02 astronomical units. So this star is pretty close, but its mass is also very high, which is 2.5 Jupiter masses, but it's very close to the star as well. So it'll create a big dip. And then there's also a very small period. So I'm just going to talk a little bit about our timeline. So for our first observation ended up being on April 17th. And that was kind of just to get things set up, basically learn about the process. And then we had two more dates, the 21st and the 3rd. And we'll go a bit more into those later. And then I'm going to talk a bit about our procedure. First off, before we were able to do anything, we had to have a little checklist to make sure that we had everything ready and that we could observe. We had to check and make sure the moon's not sticking from our star. And we also need to check for air mass of our star, the air, because if the air mass is way too high, then that means we wouldn't be able to see our star as well. And then lastly, we got to check the weather. If it's raining, snowing, anything like that, it'd be kind of hard to observe the star. Next up, once we get to the telescope, there are a few things we have to do. So for us, since we're at home, we had to open the VNC viewer, and then we also had to open our Nest Cam. And on our Nest Cam view, we would just be able to see basically what the telescope looks like from here. So like when we open the dome, for example, the dome, like we could just see the dome opening. So what we have to do when we run the telescope is we have to open the dome, and then also open the mirror cover. And then also we had to slew our coordinates. So like our star had a certain right ascension and declination. So we had to slew to those coordinates. And on our little chart, east was to the right and north was down, which is a little confusing, but we figured that out eventually. Also, in order to slew our coordinates, we also had to use a finding chart. Along the middle here is our star, Qatar-2. And basically we would just use this finding chart to figure out where exactly we want to put our telescope, since the RAN deck of the star is not always completely accurate. And also, when we slew our coordinates, we can only go 2 hours past the meridian, because otherwise we might break the telescope. We definitely don't want to do that. Yeah, now we've slewed our coordinates, then we basically take 10-second exposures of the star. So that means we get a picture every 10 seconds, then we have a bunch of pictures. And just as we go, we have to have an observation log to mark down like when we started, when we finished, the observations we had. And then last off, we have our data. So now we have a bunch of images. And we used Astro Image J. With Astro Image J, we used multi-aperture photometry, which basically takes images of all of these stars. So for example, I have these 3 points, the green one being our target, and then the red ones being reference stars. We take multi-aperture photometry, which basically measures the relative fluxes of all of them with from their 10-second exposures. And so taking relative fluxes of each of these stars basically normalizes the fluxes of each of them, because let's say a cloud passes in front of us or something like that, the fluxes of all of them might drop for a bit. And we wouldn't know that unless we measured the relative fluxes of all these stars.
So now we're going to present the actual data we collected. So this is our first trial, which we did on April 17th. As we can see, the data for Qatar-2, shown in red, has no significant change in brightness. We hypothesized that this could be due to some error in the exoplanet database, which just displayed the start and end in transits. And because we only observed the last 20 minutes of the eclipse due to the 2-hour rule that Ethan mentioned earlier, a 20-minute or so error could have caused us to miss a transit. Thus, in our second trial, we accounted for a 20 to 30-minute error. Although we could only observe the tail end of the eclipse again, we were able to observe a noticeable change in flux, as you can see by the data points in blue. This also confirmed our hypothesis on the existence of an error in the exoplanet database, as our eclipse ended about 20 minutes before it was predicted. So now with this success, we were able to observe the full eclipse in about a week later. So now measuring the full eclipse, we had another success. Now we use this data to calculate the radius of Qatar-2b, given that we know the radius of the host star, Qatar-2. We did this by taking an upper and lower bound, excluding the outliers, of brightness values before and after the eclipse, and calculating the ranges and percent drops, as you can see on the slide. The relative drop in brightness is the area of Qatar-2b relative to the area of the host star, Qatar-2. So the radii differ by the square root of the relative drop in brightness, and we get a range of possible radii for a planet. Since this range of values includes the actual radii calculated by the Qatar Exoplanet Survey, which first detected the planet, we consider this to be a success. So what did we learn throughout this process? In addition to learning a lot about exoplanets, we also learned a lot about operating the telescope. This includes guiding TMO, using finding charts to find our desired stars, operating the nest cams inside TMO, and making observation logs. We also learned how to use the software Astro to perform multi-aperture photometric analysis. This program was a little finicky to operate for us, but nevertheless, we learned how to get successful data. So we would give special thanks to Phil and Nez for guiding us throughout this process. Nez was especially helpful in teaching us how to operate TMO, and Phil Choi was also helpful in just answering the multitude of questions that we had and guiding us throughout the process.
Team CMELLY's blasting off again!
Thanks for watching.